In this slides, I want to discuss some of the set operations. The first operation will be the complement of the set of any set. So for the definition, let U be any universe. So U will denote my universe, and A is a subset of U. Then we can define a new set, and this set will be called the complement of A, and it is denoted by A complement upper square or over line A. So what is the definition of this set? It is the difference between the universal set and the set A itself, which means that I am taking all elements in my universe where these elements are not in A. Okay, so whenever we have a universal set is known, or it can be figured out from the examples or the problem you are working with, and for this set, which is a subset in the universe, I can form a new set, a complement. It's denoted by this one, or over line of A. It is a new set, and this new set is taking all the elements which is not in the universe, which is not in A. Here are some examples to illustrate this definition. The first example, I take my universe to contains only these 5 elements, 2, 3, 4, 5, 6. I take A to be contains 2 elements, 2 and 4. We see that A is a subset of my universe. Now, A complement is a new set where I take all the elements in the universe which are not in A, which means simply that we are taking 3, 5, and 6. So when A is equal to this set, the complement is equal to this set. Here is another example. My set here is a set of real numbers, and I take A to be interval from -2 closed, from -2 to 5 open. So the complement of A will be the new set with a set of all elements from -infinity to -2. I cannot include 2 because 2 is in A. Union the 5 because 5 is not in A. So here is a closed interval until infinity. The third example, we have also the universe is a set of real numbers. So the complement of the set of rational numbers is the set of irrational numbers. So the set of irrational numbers I can denote it by the complement of the set of rationals. Okay. Now it's obvious that any set and its complements are disjoint sets. These are some of the properties we'll discuss in the next slides. So what is the properties of the complements? Let U be my universe, will denote my universe, and A is a subset of U. Then A union A complement will give me all my universe. This is the first property. The second property, A intersection the complement is equal to the empty set. That is, there is no common elements between A and A complement. And the second one, it says that the union of these sets gives me all the universe. Let us prove this theorem. And in this proof, I will explain 2 proof methods for set equality. To prove the first equality here, A union A complement is equal to U, we use a 2-parts proof. 2-parts proof means that I have to prove that I have to show that A union A complement is a subset of U, and then prove that U is a subset of A union A complement, and that means these 2 sets have to be equal. By definition, we know that A complement is a subset of the universe, and here we have A is a subset also in the universe. That means what? That means the union of these two sets have to be a subset of the universe. This ends the first part of the proof. Now to prove that U is a subset of the union of A and A complement, we take X belongs to U, and we have to prove that X belongs to A and union A complement. Yeah, but since X belongs to U, then X is either in A or X is not in A. This is a tautology. This statement is always true because we have the statement and or it is negation. But that means X belongs to A or X belongs to A complement. Because if X is not in A, that means it is in A complement. Thus, X is in A union A complement, and this is the definition of the union. So if X belongs to A or to A complement, that means X belongs to the union of the two sets. Thus, since X belongs to A union A complement and X is any element in U, that means U is a subset of A union A complement, and therefore by the two parts, first we prove that A union A complement is a subset of U, and then we prove that U is a subset of A union A complement. Thus, these two sets have to be equal. Now, we go to prove the second statement. The second statement says that A intersection A complement is empty, and that means they are disjoint sets. And here we'll use proof by contradiction. Always I like to use proof by contradiction where my statements involve the empty set. So to use proof by contradiction, I need to find the negation of this statement, and the negation is easy. It is A intersection A complement is not empty. So I begin my proof by assuming that this set A intersection A complement is not empty. So I assume that A intersection A complement is not empty. But what that means? It means that we can find an element X belongs to A intersection A complement. Now I use the definition of the intersection. So X is an element in A and X is an element in A complement. This also implies that X is an element in A, and since X is not an element in A complement, that means X is not an element in A. And this gives me a contradiction. That means my assumption A intersection A complement is not empty is wrong. So A intersection A complement is supposed to be empty. Here we discuss property of the complements, but now these properties involve two sets instead of just one set. Let U be the universe, and let A and B be subsets of my universe U. Then the difference between the two sets can be written as the intersection of the set A intersection the complement of B, the first property. The second property says that the intersection A intersection B complement is equal to the first set A complement union the second set B complement, and this law is called De Morgan law. De Morgan law is two parts, so also we will have A union B complement is equal to A complement intersection B complement. This is the second part of the De Morgan law. We'll prove here only the one about the complement of the intersection. In the proofs, I will use two methods, two parts proofs, as we said in the last example, and the biconditional proof. So for the first one, I will use the two parts proof. I will begin the proof by showing that A difference B is a subset of A intersection B complement. So I will take an element on the first set and I show that this element will be in the second set. So we take X an element in A difference B. Then by definition X belongs to A and X is not an element in B. But this further means that X is in A and X is not in B means that X belongs to B complement. But this is using the definition of the intersection, this means that X belongs to A intersection B complement. So I take an element in A difference B and I found this element is in A intersection B complement, and that means A difference B is a subset of A intersection B complement. This proves the first part. The second part, we wanted to prove A intersection B complement is a subset of A difference B. So I will take an element in A intersection B complement and prove that it is in A difference B. So take an element Y, and this element is in A intersection B complement. Then Y belongs to A and Y belongs to B complement by definition of the intersection. And this means Y belongs to A and Y is not in B. This is the definition of the complement of B. But this statement here is also the definition of the difference. So Y belongs to A difference B. And thus we take an element in A intersection B complement and we find that this element is in A difference B. That means A intersection B complement is a subset of A difference B. Now the two parts here, 1 and 2, implies that A difference B are equal to A intersection B complement. For the second statement, we want to prove A intersection B complement is equal to A complement union B complement. I will use biconditional proof. So X belongs to A intersection B complement if and only if X is not in the intersection of A and B, if and only if the negation of the statement is true, so it is the negation of X is an element in A intersection B, if and only if the definition of the intersection, the negation of X belongs to A and X belongs to B. And now I use de Morgan law for logic, and this statement if and only if X is not an element in A, or the and we change to or X is not an element in B, if and only if X is an element in A complement, or X is an element in B complement by definition of the complement, if and only if X is an element in A complement union B complement. This we use here the definition of the union. So X is an element in A intersection B complement if and only if X is an element in A complement union B complement. That means what? That means these two sets have to be equal. So one direction means that A intersection B complement is a subset of A complement union B complement, and if I go in the other direction, it means that A complement union B complement is a subset of A intersection B all complement. As an exercise, you can try to prove the first statement here, A difference B equal to A intersection B complement, by using also biconditional proof. Now we'll discuss another operation to produce new sets from an old sets. This operation is the cross product of two sets. It relies on the notion of ordered pair. So if we have a pair of elements A, B, these pairs of elements will be equal to a pair of elements C, D, if and only if the first coordinates, we can say A is equal to C, and the second ones also are equal. B is equal to D. So if we have two sets A and B, the product or cross products of A and B, it is a new set denoted by A times B, or we just read it A cross B, is simply the set which contains all pairs of elements AB such that the first coordinates is in A and the second coordinate is in B. Here is an example. So if my set A contains two elements AB and the set B contains three elements 1, 2, and 3, then A cross B, it means that I have to list all the pairs, or it is the set of all pairs where the first coordinate is in A and the second in B. It is not hard to figure it out here because my sets are finite. So it will be the elements A1 and A2 and A3, B1, B2, and B3. So the first coordinate is in A and the second coordinate is always in B. This gives me 6 elements. While B times A, it means that B cross A, it means that the first element have to be from B and the second element or coordinate is in A, and this gives me a different set of elements. So when I list them, I find that I have 6 elements. Now we speak about the properties of cross product. So let's take 3 sets. So we have A, B, and C are sets. Then the set A cross the intersection of B and C is equal to the set of the intersection of A cross B with A cross C. So the first one, you take the intersection first of B and C, and then you do the cross product. While the second one, you do first the cross product, A with B and A with C, and after that you do the intersection. You can see that this kind of operation is not new to you. We call it always the distribution law. You have two operations, cross and intersection, and what you do is you distribute the cross over the other operator. So we have A cross B intersection A cross C give you this one. It is a distribution law. Now I prove this theorem by using biconditional proof. So we'll take an element X and Y because this is a cross product. So all elements will have this form X and Y, where X belongs to A and Y belongs to B. So this statement happens if and only if X is in A and Y is in the intersection. But that means also if and only if X belongs to A and the definition of intersection means that Y belongs to B and also Y belongs to C. Now this happens if and only if I just write X belongs to A twice. So this happens if and only if X belongs to A and Y belongs to B, and also X belongs to A and Y belongs to C. But this means, the first one here, it means that if and only if X and Y belongs to the cross of A and B, cross product of A and B, and XY belongs to A cross C. So if an element belongs to A cross B intersection C, then it belongs to X and Y belongs to A cross B, and X and Y belongs to A cross C. Okay, and this is the definition of the intersection. So we can add here, if X, Y belongs to A cross B intersection A cross C. Okay, so what we have A cross B intersection C is equal to A cross B intersection B cross C. Now I want to introduce a few formulas to count elements on finite sets. So recall that if D is a finite set, that means it has a finite number of elements, and the number of elements is denoted by D between straight lines, or D with two overlines. And what that means, this one is a set and this one is a number. It is the number of elements in the set. And to remember that the number of elements in the set makes sense only if D is finite set. Now we have a theorem which says that if A and B are finite sets, then the number of elements in the union is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection. So we have a formula for the number of elements in the union. Also, the number of elements in the cross product of A and B is equal to the number of elements in A multiplied with the number of elements in B. So we have a formula for the number of elements in A cross B once you know the number of elements in A and the number of elements in B. And the last one is about the number of elements in the power set. Recall that the power set is a set of all subsets of A, and the number of elements in the power set is equal to 2 power A, the number of elements in A. In particular, what we have from this theorem is that if A and B are disjoint, which means that the intersection here is equal to pi, then the number of elements in the union is just the sum of the number of elements in the two sets. We will not prove this theorem in these slides. We will take them as axioms, so you have to understand them and use them in solving exercises. Here is an example. So let A and B be two sets. And the number of elements in A is equal to 2, and the number of elements in B equal to 3. We want to find the number of elements in the power set of A cross B. So to solve this example, I need two formulas. First, the number of elements in the cross product is equal to the product of the number of elements in the two sets. So we have the number of elements in A cross B is equal to 2 multiplied with 3 is equal to 6. And the number of elements in the power set is 2 to the power of the number of elements of the set. So we find that it is 6, so the number of elements will be 2 to the power 6. Here is another example. Suppose that I have A and B are two sets. I know that the number of elements in A is 10 and the number of elements in B is 6. So, and the number of elements in the union is equal to 12. So we want to find the number of elements in the intersection and the number of elements in the difference by using counting formulas I give in the previous slide. So the first law tells me that the number of the elements in the union is equal to the number of the sum of the numbers of elements in A and the elements in B minus the number of elements in the intersection. I use this formula to find the number of elements in the intersection because I know that the number of elements in the union is 12 and in A is 10 and in the B is 6, but this one is unknown. So solving these equations, I find that the number of elements in the intersection is equal to 4. Now to find the number of elements in the difference A difference B, I notice that A is always equal to A difference B union A intersection B, and A difference B and A intersection B are disjoint sets. That means the number of elements in A is equal to the number of the elements in the first set, A difference B, plus the number of elements in the intersection, A intersection B. Now, I know the number of elements in A, which is 10. I just substitute. The number of elements in A difference B is unknown, and this is what I want to find. But the number of elements in the intersection, I know it. It is 4. And solving this equation, I find that the number of elements in the difference is equal to 6.